Hi, George Romanic here. In today's video we will talk about the height of isothermal atmosphere. That is, an atmosphere in which temperature does not depend on the altitude. I described this concept of isothermal atmosphere in my previous video, and we also introduced a parameter called pressure scale height. We know that pressure in such an atmosphere exponentially decreases with the altitude, but the rate of this exponential decrease can be different and is described by this pressure scale height. In addition to determining the height of such an atmosphere, we will also connect this concept with completely different phenomena from electromagnetism, namely discharging of a capacitor. How is it possible that these two things are related? Well, actually they are not. But to answer that question, I will quote a great man, Richard Feynman. He said, "Same equations give same solutions." Remember that rule and you will be much better at physics and atmospheric sciences. Let's check out this problem. In previous video, we derived barometric equation that describes how pressure decreases in isothermal atmosphere, and we saw that pressure is Ps e to the power of minus gz over r dt. Ps is the surface value of the pressure, P is pressure at height z, g is gravitational acceleration, Rd is gas constant for dry air, and T is temperature in kelvins, but temperature is constant here, isothermal atmosphere. However, we also introduced the substitution Hp, that is Rdt over g, and therefore this equation becomes P is equal Ps e to minus z over Hp. So, just to graphically represent what I'm saying here is we have surface of the Earth where we have z equals 0 and surface pressure Ps, and somewhere here we have height z, so height increases like this. We have height z and pressure P. Temperature is constant. Also kindly recall that in previous video we calculated actually this this is called pressure scale height. We calculated Hp for different values of temperature, 15 degrees Celsius being the surface temperature of the standard atmosphere. Check my video on the standard atmosphere. Knowing all this, let's ask ourselves a hypothetical question. What would be the upper height of an imaginary atmosphere in which temperature does not change with height? Well, then this figure becomes the following. We would have surface of that imaginary Earth, that would be z equal 0, and we would have some surface value of the pressure. We would have some height, let's call it zt, z top, and at that height pressure would be 0, and this is the vertical axis z. Along this height temperature would be constant. Well, if we implement information from this graph into this equation, we will get that 0 is equal Ps e to negative zt, z top over Hp. Or simply, if we divide by Ps, given that Ps is not 0, 0 is equal e to the negative zt over Hp. But wait, you might say. This is impossible. This function is never 0. And you would be right. An atmosphere in which temperature does not change with height does not have the limit where pressure is equal to 0. This exponential function never collapses to 0. It collapses to 0 at infinity. In other words, if this is a graph of a function, let's say z, and here, function f of z, and here is an independent variable z, then this is the graph of the function e to the negative z. Z needs to tend to infinity in order for this to touch the z-axis. In other words, there is no finite height at which the pressure vanishes in the isothermal atmosphere. If you are electrical engineer, then I hope you will see big similarity with the discharging of a capacitor. You will remember that if we have a capacitor and here is time and here is current, we start with some initial current, let's say I naught, and capacitor is discharging like so. But it will take infinite amount of time before it completely discharges. In other words, capacitor will never completely discharge because the functional dependency of a capacitor is exactly like this, exactly, but instead of height and some scale height, we have time and some scale time for this capacitor. So you can see similarity between atmospheric sciences and electrical engineering in this particular case over here. One can only hope that you will remember this concept that same equations give same solutions. It will help you a lot, because if you encounter a problem, a phenomena that you don't understand properly, but you see that equation that describes it is same or has the same form as some other equation that describes phenomena that you already understand, then you can make relationship between these two. I hope what I just said makes sense in terms of English. If not, listen it one more time. Until next video, goodbye.